Hi, this is Mr. Yeager for AP Physics 1. I'm here today trying to help out doing a couple problems so you at least can see some problems worked out with either work, and I have one that's a brief work energy theorem problem. So for this particular problem here, what it's basically saying is we have this block of mass 2.5 kilograms pushed 2.2 meters along a frictionless horizontal table by a 16 Newton force directed 25 degrees below the horizontal. Okay? So, I should probably draw this out. I have this box, okay, 2.5 kilograms. I should draw that bigger next time. All right, 2.5 kilograms. It has a force that's directed 25 degrees below the horizontal. So some force F, I'm going to call it F applied, at an angle 25 degrees below the horizontal. Okay? And it's moving 2.2 meters. 2.2 meters. Okay? Now, could you have said that this object was moving to the right or left? I mean, sure, doesn't really matter. Okay? So let's get to the first question finally. Is the work done by the pushing force positive, negative, or zero? All right. So how do I approach this? Again, if work is done in the same direction as the force, then it's positive. If the force is applied opposite direction of the motion, it's negative. And if the force is basically exactly perpendicular to the direction of motion, it will be zero. So the thing is here, I know some people would initially go, well, FA, that's pointing at an angle while it's moving horizontally. All right. So is that doing no work? Should my answer be zero? All right. But no. The thing is here, what it's asking is this force applied doing any of the work? Is it helping move the object forward? And the answer to that would be yes. So the answer would be, it would be a positive work being done. And the justification for that would be, it's not the whole F of A. That's not pointing in the direction of motion, but it's going to be a component of that force. And so that would be our justification. A component of F of A points in the same direction of motion as the displacement. So that would mean it's a positive work being done. So now, part B, calculate the work actually being done by the pushing force. This is where you got to be careful. Again, people can mess this up and go, still get the first part right. Say, yes, FA is doing the work. So positive, blank, blank. You know, it's moving in the same direction as the displacement. But the thing is, we're doing work. What does work equal? It equals F times D. That's fine. I mean, that's in there. It's the force parallel to the displacement. But the thing is F of A parallel to the displacement? The answer is no. And so I need to move to FD cosine theta. The Fx is parallel with the displacement, which would be the cosine with the hypotenuse, the adjacent component, and therefore would equal, let's get these numbers out here, 16 times 2.2 times the cosine of 25, right? Yeah, 25. And that equals 32 joules. Okay, 32 joules. All right, so pretty close to the total amount, but not total. If it was 16 times 2.2, it would be a little bit greater. All right, so that's part B. Let's keep moving forward then. Okay, part B. Part C, it's continuing the problem. Calculate the work done by the normal force exerted by the table. Okay? Well, let's look at that again. Wait a minute. Normal force. Normal force would be pointing up when the displacement is to the right. What does that mean? The answer is 0 joules of work. Why? They are not pointing in the same direction. They are perpendicular to each other. The force and displacement are perpendicular. Okay? Force is perpendicular to the displacement. Calculate the work done by gravity. Same thing. Gravity straight down. The displacement is to the right. Guess what? That's 0 joules of work again. And they'll ask you those questions. I mean, that shows that you conceptually understand that the force must be parallel with the displacement. So it's a perfectly good question. It's not meant to be like, oh, gimme. All right? Hopefully it becomes a gimme for you. All right? And now we're bringing that now back into the work energy theorem. Assuming the block started from rest, calculate the speed of the block after 2.2 meters. After 2.2 meters. All right? So I do help my students out here because this is an early worksheet. Sometimes and actually for this one I haven't introduced the work energy theorem yet. So if you're doing this after we look at the work energy, it's pretty straightforward. But what we're doing here is we're going, okay, well, technically the work energy theorem would be, that's not it, initial potential energy plus initial kinetic energy plus work external equals final potential energy plus final kinetic energy. And this is a good problem to look over just because we can go in detail. Probably don't need to go this much detail when you actually do the problem. The thing is, we know we're on a horizontal surface, so potential energy doesn't change. Okay, even though it says we're on a table, it's not going to change. So to get rid of that. The object started at rest, so the kinetic energy is zero. You can see we started with zero mechanical energy. There's zero mechanical energy. So there must be some sort of work to make sure the object then receives energy. And so you can see the formula will be work external equals kinetic energy, final kinetic energy. Well, we found the work external in the last problem. It's 32 joules. This will equal 1/2 mv squared. Okay. And we know the mass of the object. 32 joules equals 1/2 times, what's the mass? 25? 2.5. 2.5. Okay. 2.5 kilograms times v squared. V will equal 5.1 meters per second. Okay. So this object starts at rest. When 32 joules of work is applied to the object, it'll start moving at 5.1 meters per second. So one more problem to go with this video. All right, we have two identical arrows, one with twice the speed of the other, are fired into a hay bale. Okay. Assume that hay exerts the same friction force on each arrow. Wow, I can't talk. Arrow. Use the work energy theorem to determine how many times farther into the hay the faster arrow will penetrate. Okay. All right. So this is a classic AP one because we want to relate variables here, and I know this is one that my students always get so frustrated with trying to figure out. All right. So we're using the work energy theorem. We're saying one arrow is fired with twice the speed, twice the velocity. Same frictional force is applied by the hay bale. And we're going to use the work energy theorem to determine how many times farther. So we're looking for displacement. Okay, delta x, however you want to write it. Okay, d or delta x. How much farther will the faster arrow go into the hay bale than the first one shot? Okay. So again, I provide some help here. So I mean, this is one where it's like, okay, well, if help's not given, we should still lead to this. All right. So we're looking at the idea that work external will equal the change in kinetic energy. Okay, the change in kinetic energy. All right. So for this one, because the potential energy we're saying is staying the same. Okay. With this one, basically we're breaking it down to the fact that, let me think about this real quick. What we're going to do is we're going to break this down to work is equal to force times distance. Because what's going to happen is, here's your hay bale. The arrow is going to go into the hay bale perfectly horizontally. Don't make it any more difficult than you have to. It actually doesn't have to be perfectly horizontal, but let's just say it is. Okay? It's going to go into the hay bale. What's going to be acting on the arrow as it enters the hay bale? That would be, change colors here so we get a little bit different contrast here. That would be friction. It's going to act exactly opposite to the motion. So what happens here is we actually have some initial kinetic energy. Technically, my formula would be KEI plus work external actually equals 0 because we're saying it has no more energy. Okay, the potential energy doesn't change. We're not going to pay attention to that one at all. And so we know the work external is actually negative. And so the initial kinetic energy equals the work external. The work is removing all of that energy. And so what I have here is this is the frictional force. Technically, I'm not going to make it negative anymore, it's positive. It's frictional force times the displacement equals 1/2 mv squared. All right? So I'm going to rewrite that to get rid of some of this stuff. Okay? So, whoops, that's not what I wanted to do. Okay, let me erase that. Okay? Let's get it clear here. We're doing work external equals initial kinetic energy. And so F of F times D equals 1/2 mv squared. And so how do I figure this out? I want to know how many times farther in will the second arrow that goes twice the speed go. How I always approach these problems and how I would try to encourage students to approach is we're going to eliminate anything out of this formula. Anything out of this formula that is a constant in both situations. Obviously, you can plug in numbers, you can create numbers, but the whole idea is you need to make sure you're working quickly on the test. And so we're going to eliminate anything that is the same for both arrows. That would be F of F. Acts the same on both arrows. It's the same mass. I'm going to multiply both of them by 1/2 the same. So that leaves me with a relationship between distance and velocity with this. Distance will equal velocity squared. And so the big question is, if I double the velocity, if I double the speed, I do that before I square it. Okay? I want my formula to go back and look like this. It's basically the coefficient in front of both of them is 1. So they have to have the same coefficient after the problem. And so what happens here is this becomes 4v squared. What coefficient did I add on the velocity side? 4. So this will be 4d. So how much farther will the arrow penetrate into the hay bale? It'll penetrate 4 times as far as the first arrow. All right? So that's one problem. Thank you.